Hello everyone. For the past few months, I've been working on this, an automated life detection subsystem for my University Mars rover. And while I haven't documented the project in the same way as I will do in this video, there are many videos, pictures, and a detailed description on my portfolio, samrosenportfolio.com. So one of the life detection chemical reactions on board needs to be 100 degrees Celsius. So this is the perfect opportunity to use PID control. I'll link a more in-depth explanation of what PID control is in the description, but simply put, you have a target value, in this case temperature, and you have your actual value. The program is constantly calculating the error difference between the two values and adjusting accordingly. While this is a super simple and easy project, I think it will apply well to larger projects like I will be doing. So let's get right into it. First, I need a way to generate heat. I'll use this cartridge heater. These are primarily used for 3D printers. They are super cheap, get super hot, and only need 40 watts, so they are perfect for this. I soldered on an XT60 connector and connected it to a VESC. This is an open source electric speed controller, usually used for electric motors, but I will use the PWM to control the voltage going to the heater. Yes, this may be super overkill, and you could probably get the same results with a cheap MOSFET and some extra circuitry, but I had this laying around already, and I like how it completely isolates the 12 volts from the GPIO pins on the Raspberry Pi. This controller is essentially 6 MOSFETs, a microcontroller, and some extra safety features. Alright, so for the PID to work, we need temperature feedback. I'll use this temperature probe along with this little board that it came with. If you don't have this board, you can just use a pull-up resistor between the signal and VCC, and you can use a 5K. This will plug into pin 4 on the Pi, and I'll use 5 volts. Pin 4 is the default one-wire communication protocol pin, but you can use any pin with some extra configuring. Alright, so let's write a Python script to test this temperature sensor. Alright, so I'm connected to the Raspberry Pi via SSH. The first thing that you want to do is turn on one-wire communication protocol. Click yes, okay. And here's the script that I wrote. It uses the W1 therm sensor library and the time library. It creates an object from the class, has an infinite loop that has a variable, and it gets temperature and prints it to the second decimal place. So let's go to the location and run it. And you can see we're getting 19.5 Celsius. And if I hold this, the temperature should increase due to my body heat. And there we go. 20, 21, 22. All right, so now that we know it works, we can hook up the heating module and play around with that. All right, so I have all the electronics set up. The VESC is running on 12 volts, and I just taped the temperature sensor and heater together for testing purposes with this polyamide high temperature tape. After a few hours of testing, I have some working temperature control. The main issue that I've been dealing with is that the system kept overshooting the target temperature by 25 to 30 degrees. I've been able to narrow this down to 2 factors. So first, I discovered that the refresh rate of the temperature sensor is not fast enough for what the PID control needs. With a refresh rate of around 750 milliseconds, the derivative of the control is basically useless data. I tried a thermocouple with its amplifier since it's supposed to refresh every 100 milliseconds, but this introduced other problems, so I decided to stick with the original temperature sensor and work around it. Additionally, I need to account for the thermal lag in the system. Even after the duty cycle drops to 0, heat stored in the heater's core continues to propagate outward from the heater for roughly 10 seconds, so the temperature keeps rising after the heater is technically off. I'm sure this thermal lag and thermal loss will only get worse once I introduce the glass vial. So, how did I fix this? Instead of relying on the PID derivative term, which is ineffective due to my sensor limitations and thermal lag, I implemented a predictive model using the measured rate of temperature change to estimate the temperature 10 seconds into the future and adjust accordingly. Using the derivative as a measure of the system's thermal momentum instead of the instantaneous feedback is working great. The system consistently settles around 100 degrees Celsius with fluctuations of approximately plus or minus 3 degrees Celsius. Alright, so in the terminal below you can see the script running, and I'll quickly explain it. So I'm using the same temperature sensor library, I'm using the simple PID library, and I'm using the PI-VESC library. Here's my target temperature of 100 degrees Celsius and my maximum safe temperature of 110. I have an overshoot time of 10 seconds, and here I'm defining the USB port of the VESC. This is the PID refresh rate, and here are the PID gains. Here are my minimum and maximum duty cycle, and right here I am defining the variable for the predictive model. I'm initializing my sensor and connecting to the VESC, and if whatever reason it cannot connect to the VESC, it's just an error. Here I'm defining a function to set the heater power, and here I'm calling some functions for the PID setup. Right here, if for whatever reason the temperature is not spitting out data, it will set the heater power to 0. And right here, if it goes over the maximum temperature, it will also set the heater power to 0 and break. Right here, I'm calculating the temperature slope. Here I'm calculating the future temperature. Here is PID control, and if the predicted temperature is over the target temperature, it sets the duty cycle to 0. Here I'm calling my function, and here I am printing some information. Originally, I taped the heater and temperature sensor directly onto the side of the test tube using the tape, but quickly observed that the heat did not spread well through the glass and created a hotspot. So I flattened this tube with a mallet to make a housing for the heater and temperature sensor to press fit into in an attempt to increase contact between the heater and glass and eliminate the hotspot. And again, I used the polyimide high temperature tape to secure the heater housing to the test tube. This improved the results, but still the temperature inside the vial is too low due to thermal losses, conductivity, and still a small contact surface. So I ordered an 18mm copper tube, and as expected, this did not fit. So I bust out the Dremel and got to work. So there we go. They fit in perfectly. And now I will cut it down to size. There we go, perfect fit. And I've wrapped everything in this gasket paper since gasket paper is a great insulator, which reduces heat loss. And there we go. I would call that a success. I'm consistently hitting 100 degrees Celsius after multiple tests. I did have to set the cartridge heater temperature to 110 degrees so that the inside of the glass vial will be 100 degrees due to thermal loss. And last but not least, here's the heating module integrated with the rest of the system. Alrighty, if you have any questions, please feel free to leave them in the comments down below and subscribe to see more of my upcoming videos. You can also check out more of my projects at samrosenportfolio.com. Thanks for watching.